Yes. It's a pleasure now to drill down a little bit further into FlexSNG with a round-table discussion on de-risking FlexSNG. So a capital-intensive process. So everyone remembers everything Ilkka said this morning. Thank you for that excellent overview. And I think also, as we said in the different presentations this morning, that if you're making a biofuel, developing a biofuel process, it's capital intensive. Small risks look very large. If you're spending that much money to make it work, then there have been spectacular failures. And David did a great review of that. So the stakes are high. De-risking is very important as you're moving up in TRL, and that is really the pleasure of this project. How is it happening? Well, Ilkka also introduced Horizon Europe funding for the project. We don't have all 95.5 billion euros, which is what that program, the size of small GDPs, I would say, of some small countries. But it's impressive, but it's also essential if we're ever going to make the bioeconomy happen. And even if you have all the money in place, the de-risking still needs to get done. And that's what today is about. So we have 6 talented roundtable speakers. This is the order in which they'll speak. Our first speaker is Minna Kurkela of VTT. She's only been there 30 years, so she knows a little bit about what she's talking about. And she's sort of our keynote panelist. She'll take a little bit longer and go back into history and some of the challenges. Her research field is gasification and gas cleaning and thermochemical conversions, and she's worked on many EU projects as a researcher, and she's our boss in FlexSNG, but you don't find a nicer boss. And I'll go through all the introductions and then get out of the way so we can move forward. And then next up, potentially next up is, excusez-moi, ça avance pas. Merci. There we go. So the next speaker is Francesco Mondi. He's a development engineer at D2 and a lab manager. Let me just find that. Working in the Department of Energy Conversion and Storage. His main areas of interest in research are high temperature fuel cells, if you can believe it, and electrolyzers, and the design and upgrade of test facilities of the high temperature electrochemistry laboratory in the department. And he's going to talk to us all about membranes today in his presentation. The third speaker is Mikael Rönnqvist. He's the younger of the 2 Rönnqvists that we're seeing today. He's a professor in industrial engineering at Université Laval, has a Canada Research Chair in operations research and natural resources, and his research interest is in the use of optimization and industrial applications. And he's going to talk to us about procurement of biomass and coordinating value chains. The next speaker is Karol Witkowski, a research engineer at the European Institute for Energy Research, or EIFER, in Karlsruhe, Germany, where we held one of our FlexSNG meetings just a couple of years ago. He specializes in biomass treatment, particularly in thermochemical conversion processes. His experience in both industry and science allows him to share valuable insights on biomass valorization. And he's going to talk about de-risking biochar production and its potential value. The next speaker is Tunet Olivier. She's a chemical engineer with bioprocessing. She's worked in the renewable energy sector, where she gained expertise in business development, project management, engineering design, and consulting. She has a keen interest in the bioeconomy and in biorefineries in general, and she's honing her skills by pursuing a PhD at Polytechnic in industrial symbiosis, and she's going to talk about industrial symbiosis in her presentation. And last, but certainly not least, is Kostas Atsonios. And I got to say, a really important person in this project. He leads a group at CERT, which is the Center for Research and Technology Hellas in Greece, and he's doing the modeling and technoeconomics of FlexSNG and interpreting if you will, sparse economic results, which is the sort of results we get from gasification for their interpretation. Very talented. So let's get going with you, Minna. We'll go through all 6, and then the flurry of questions will begin.
Good morning, everyone. I will talk about VTT's research challenge, and our focus is here the flexible gasification process, where we co-produce the biochar and synthesis gas in a plant that can be operated in 2 modes, in a maximized gas yield mode and a co-production mode. Then also the plant has the ability to switch between these operation modes based on the market demands and price signals. And first, some background for this flexible gasification process. VTT has a very wide gasification fuel processes development, and we have key steps here. Gasification in CFP gasifier, which is pressurized steam oxygen, and then followed by filtration, hot filtration and catalytic reforming. And then the final gas can be utilized in, for example, FT products, methanol, SNG, and hydrogen. So several applications. And we have developed and demonstrated this together with Sumitomo SFW, this process, and also wide experience with these different kind of fluidized bed gasifiers like CFP, BFP, and then modified BCFP, which I will come later to tell you what that is. Okay, that was the background. Then we enter to our fluidized bed gasification technologies. So in this FlexSNG, we had 2 alternative gasifier designs, which we examined in the co-production of biochar and syngas. First, when this FlexSNG process was planned, our initial assumption was that the ordinary CFP gasifier process would not be suitable for this biochar production. And in this CFP, the feedstock is fed here above the dense bed. Here's the bed. And then it's pyrolyzed in the upper part. And we reach a high carbon conversion. And the recycling charcoal meets here, again, the oxygen at the bottom of the bends. So there would not be produced biochar in this CFP. And we also assumed that we would reach a high tar content at low temperature gasification, which would block the filter and make soot formation in the reformer. And so the biochar would be recovered in the CFP gasifier as a filter dust. Then our suggested solution was the BCFP. So the BCFP is a combination of BFP at bottom here and then CFP at top. So it has benefits of both technologies in the same gasifier. The bed is operated at lower temperature and upper part at freeboard at higher. We use the secondary steam oxygen here to put the higher temperature in the freeboard. Then the tar composition in upper part of the gasifier would be produce stable filtration and easy reforming. in this bubbling circulating fluidized bed. And we assume that high quality biochar would be produced from the bottom as from this gasifier. So these were our assumptions. Then we entered to our gasification process development work. We had 3 one-week-long test campaigns in recent years using bark, straw, and cleavewood as a feedstock. And these both alternatives, gasifier designs, BCFB and standard CFB, were assessed for their suitability in this co-production of good quality biochar. And here you can see our test facility, which we used. Then we produced the biochar, and it was delivered for further characterization to one of our project partner, to EIFER, Germany, to see how was it like. So first we entered the BCFB mode. So we achieved a very flexible operation in that case. And then first we used a very high temperature gasification near 900. And as you can see, we reach a high carbon conversion in this case. Then we reduced the temperature near 700. And the carbon conversion was low, reduced in this case. And in this case, 700, most of the charcoal was treated to fine dust, and it would be captured as a filter dust in this case. But then the last set point was done in a lower temperature near 650. And it was the case that we managed to get a biochar like this one, but it also entered the filter dust, the gray bark here. And the operation was unstable in this low temperature gasification. And we have to remove our bed material totally, in this case, in low temperature gasification. And that took very much time, and it was kind of difficult to shift between the operation modes in this case, because the bed material must be changed. But the results indicated in this case, when we delivered the biochar to characterization, that the filter dust and biomass derived biochar were fairly similar in terms of the quality. So the results were kind of encouraging. Then we entered to CFB mode. It's not working. Now it's moving. Yeah, in the CFB gasifier, thanks. So we reach again flexible operation under both operation modes, as you can see. And the biochar yields were increased when the gasification temperature was reduced. And this case, the biochar was recovered as a filter ash rather than do the gasifier biomass. So it was in filter ash. But in this case, CFB mode, it was very easy to shift between operation modes, and it's highly reliable and stable process. And we carried out a very successful test with all these feedstocks. Also, the filter and reformer worked well. There was stable operation achieved, and the catalyst worked well. There were Johnson Matthey catalyst, even at low temperature tests. So the conclusion was that these both gasifier modes could be adapted to FlexSNG, but if we take into account the industrial perspective and scalability of this technology, the conclusion is that the standard CFP gasifier was more capable of producing the high-quality biochar. It was less complex, the reactor design, and would work well. So we selected the CFP for the further validation test, which are now ongoing. And in addition, this CFP gasifier has the following benefits. It's industrial proven by Sumitomo SFGW gasifier design, and it has been demonstrated in syngas application. Also, the operation flexibility is better in this case, and it's easy to transit between this cooperation and maximized production modes. And also the differences in biochar quality between these CFP and BCFP designs were not as significant as we expected beforehand. Although we got a high yield in BCFP mode biochar also. And then the filter and reformer were handled even high tar loads without no signs of soot formation. And now we enter to our validation test campaigns, which are ongoing. We have now carried out around 160 gasification hours totally, and they will continue in this spring. We have already used very challenging waste-derived fuels and also co-feeding biochar together with waste. Okay, I think that was all from my side. Thank you.
Yes. Hi, everyone. Thanks for being here. I'm Francesco Mondi from Technical University of Denmark. And today I'll show you some results of our tasks in the project regarding the oxygen transport membranes that are used in this project for the production of oxygen that feeds part of the biomass gasification process. So a few words of introduction of the Technical University of Denmark and my department, the Department of Energy Conversion and Storage. We deal with several research topics that span from fuel cells, power-to-X and electrolysis, carbon capture and utilization, gas separation and storage, batteries, flow batteries, and thermal energy. So we cover several topics for energy conversion and storage that tackle the problems that our society is facing nowadays. And in particular, in this project, we try to apply the OTM, oxygen transport membrane technology for oxygen production. So these membranes are ceramic high temperature membranes that are capable of transporting oxygen from one side to another of the solid membrane by an electrochemical principle of operation. So we can obtain pure oxygen on the permeate side of the membrane. And the driving force is the different partial pressure of oxygen on the two sides of the membrane. And as you can see, the membranes are obtained in this hairpin as we call it, kind of shape. And they are produced from Praxair, that now is a society part of the Linde Group. We started testing the membranes in our single tube performance evaluation rig. So it's small samples of about 5 centimeters of length. And we characterized the operation of these tubes, flowing air on the outside of the membranes and reducing gas on the inside. And we tried both with pure hydrogen and a composition that simulates the syngas that is produced by the gasifier. And after mapping the performance of the membranes, we managed to obtain the target of the project, which is an oxygen flow of about 3 milliliter per minute per square centimeter of active area of the membrane at a temperature of 950 degrees Celsius. And we got results above the target of the project in both feeding conditions of hydrogen and the simulated syngas. After that, it was time to go bigger and implement the membranes in a full-sized reactor. So we designed the reactor in this radial configuration of the tubes that you can see in the cut view of the reactor. We produced it, and then we, as you can see, the operating parameters are temperature of about 900, 1000 degrees that grows from inlet to outlet, and it generates a heat power of about 1.1 kilowatts. The reactor was then installed in a test rig that can be operated autonomously, but can be, of course, interfaced with the gasifier. And then the rig was shipped to Finland and interfaced with the gasifier, so it can receive the gas directly from the gasifier during operation. And the results that we obtained that were very good. We are still testing. We are 2 test campaigns in, and we managed to obtain stable operation of these membranes for above 100 hours, and a performance in terms of oxygen transport that is within plus minus 5% of the reference levels that we measured in laboratory condition. The very good very good result that we obtained is that the membranes are highly tolerant to the impurities that are contained in the gas, so sulfur, chlorine, that we foresee that they could be a problem for the membranes, but for now it seems like they are quite stable and tolerant to this level of impurities. And they managed to achieve a conversion of tar above an average of 90%. We also checked the resistance of the membranes to cycles of oxidizing and reducing conditions, and they also managed to withstand this cycling without having particular signs of degradation of performance. So the integration was a bit challenging, but we also have future challenges. We have to test the long-term durability of the OTM. So in terms of thousands of hours, that will go above the project target, but we plan to continue testing them. And we plan of trying to improve the conversion of aromatic molecules such as benzene and naphthalene by introducing a different catalyst or varying the residence time of the gas inside the reactor. And overall, on top of that, we're gonna test probably also pressurized operation of the reactor, because now we operate just slightly above ambient pressure. And also check some alternatives for the materials utilized in this reactor design to improve the coking resistance of the various parts of the balance of plant. And that's all from me.
Okay, so my time. When we are looking at this project, when I'm developing our decision support systems, I typically look at one chain at a time, so forest by itself or agricultural by itself. Now, of course, in FlexSNG, we have this super idea to put everything together to make it more complicated. And of course, that the potential for savings are higher, but it also makes some complications. So I just briefly going to go through some of the challenges that we have that you typically not see when you are doing one of them. So for sure, one of the critical one is the seasonality. So if you go to agriculture, we know that depending on the crop type, you might do 1, 2, or maybe 3 harvests during the year when there's a high intensity in doing the harvesting. If you would go to forestry, for sure it's more slow term. You'll do a bit more harvesting in the winter, but more the collection of residues more in the summer. So you have a bit of seasonality. For the municipality waste, for sure it's similar. You have more demolition, more changing of houses in the summer, so you have a more supply in that time. So how do you deal with that? If you're in one chain, you do it by managing your inventory and your production. When you put the 3 together, it's even more complicated. So inventory is a key aspect, and we need to see where can we have bio hubs, where can we have terminals. We need to decide where do we do shipping of different assortments, and how do we store them. But because of this analysis, we also need to keep track on the quality of it. So we need sensors to have that. So that's one thing. The other one is what I call a value chain coordination here. So even if we are putting these 3 together, they're not by themselves anyway. So if I will go to forest residues, it's not like I can go and say, I'm going to have the residues from the forest, because I need to coordinate with the guys for the sawmills and the paper mills. So there's another coordination there. And of course, it's a similar thing on the agricultural side. So on the forest, I might need to coordinate with a number of forest companies together with the government to get the supply in time and how it's accessible. On the agriculture side, it's even more complex, because it's not one I coordinate with. Depending on the value of this on the year, there are certain crops which has higher value. So when you have thousands and thousands of farmers, they are the one making the decision what crop to have for the next year, and that's a coordination through various sort of market prices. So we need to look in that way too, and once we have done our savings, it's sort of for the entire the 3 chains, and we need to do some compensation. So if the forests are the one that are backing to make sure that the agriculture can balance better, yeah, maybe they should have more of the savings. So there are different ways to compute the savings depending on your impact on the total savings. So there are development of that. For the transportation, so if we look at forestry, there are transportation companies that have specialized trucks for doing that, if it's logging or wood chips, and the same thing for agriculture and the municipality waste. Now, when we're going to put these together, because we want to use a common resource for this, there's a need to do the coordination. So of course, some of the trucks can also work in the other chain, but others cannot. So we need to do that. And for some of the trucks, it might be that we need to put some reinforcement on it, or we need to cover it, or other things, or we might need to clean it if we do the bark and then the chips. So these are things that are not traditionally in the models we are using. So we need to develop that too. The other one is more the planning horizon evaluation. So when we are looking at case studies, we want to be able to compare with what happened before. But for sure, when we're looking backwards, we can look at the transportation data and things what happens. But when we want to do, like in our case, if we want to supply a biorefinery, we also like to look forward, which means that there are other challenges, because we need to find the forecast. How do we find the forecast? Well, there are many different databases for doing that, but there are some news and we need to merge them together. The other one, the data standard, and I'm more in the forestry, and I don't know how many measure units there are for volume. There you have underbark, you have with bark, you have the green, you have the dry tons. there are 10, 20 different measures, and there are different tables to go between them. And of course, you can imagine when we have another sector, we need to put that together too. When it comes to, for example, the forestry, and if I go back to Sweden, there are some organizations like in their Biometra that have developed standards. They have tools for capturing the data and managing it. So they share with the different companies. So they really develop standards for this. So I think there's a need to do it here again, but who will do it? It's a bit of a challenge. And of course, for the coordination here, and you heard something about from the last presentation, there are some tools developed, but if you go to different companies managing the transportation, they all have their own data IT systems. And to do this coordination, it needs to be some new tools like the one we heard about, but then you need some cloud systems to operate that. And there are for sure some need to develop tools to manage, for example, what are the forest inventory, what are the agricultural inventory. So that's a big challenge for that too. But these are some of the challenges, and we are working on all those. Some are specific for FlexSNG, but there are also common, of course. So things we are working with. So I'll stop there.
Okay, I'm ready. So, hello everyone. My name is Karol Witkowski. It's a great honor for me to be here and to give you a few information about the biochar, how to make that product available for the market. I will try to keep my presentation very simple. I was asked to present only one slide, and this is what I did. I like to talk a lot, and today I would like to talk you a story about the biochar and good valorization pathways for that. Before I go to that slide, recently I found a nice series on Netflix, You Are What You Eat, and I think that's the same with the biochar. That if we think about the process of methanation of SNG, I mean, at the end, we always have biomethane, and it doesn't matter if that biomethane was produced using syngas, using anaerobic digestion, we have methane, quite simple product that we can utilize everywhere, and the quality is there. With the biochar situation is a bit different. Biochar can be produced through different technologies. Gasification is only one of them, and I'm glad that we have such a nice concept in our project that we can have this bio mode production. However, biochar can be also produced through torrefaction, through hydrothermal carbonization, through pyrolysis, slow, fast. And then even for the gasification, we got today a nice question regarding the size. I would say that we will have also a big competition regarding the biochar production from small gasifiers which are not built to provide us methane at the very end. It's just the gasifiers which will be used for direct syngas combustion, gasifiers that will be used for CHP, for gas engines. So we are talking about fixed bed gasifiers, and they can also be operated in two modes. It means that at the very end, we may have a lot of biochar on the market, but the biochar and its characteristics will vary a lot. Why? Because if we think about the process itself, residence time, the temperature of the biochar production will impact its properties. We checked, of course, in the frame of the project, if the biochar produced by us is good. Yes, it's good. I mean, it lays in the range. So now we have to define a good valorization pathway for it. So the biochar, I mean, nowadays is a very trendy thing because at first we can use it as a carbon sink, so that we just put that biochar somewhere. We can put it into the soil as the, I mean, to fertilize it, or just to do the soil remediation. However, there are some requirements that need to be met if you want to use biochar in the specific utilization. So if you'd like to put biochar to energy or to cement industry or to use it in biomaterials, everywhere there are some specifications. The problem is that nowadays there is no like standard. There is like no international standard saying that you need to produce that, that, and that, and that, and then you can go with that product to the different sectors. If you think about the biomass combustion, it's totally different, because then we have the standards for the fly ash, for the bottom ash, I mean, for the ash in general. And here we have some challenges that we have to tackle in order to have a nice product at the end. So I put on my slide 4 points. So feedstock management. Today we heard a lot about the feedstock management, how important is that to provide sustainable biomass, how to have my biomass available, how to gather it from the area where my plant is located. However, here I see the big risk of having the biomass with a very challenging composition. There will be a big competition for the biomass and its use. From the biomass, we can produce a lot. Biochar is only one of the products. We will need the biomass for combustion. We will need the biomass for liquid fuels production, and there will be like a lot of people would like to have the biomass, and then at the very end we may just take what's there. We won't have any impact on the quality of the biomass that comes to us. Recently, I even got the question from, I work for EDF Group, and we have some biomass plants. And 5 years ago, I kept asking the guys, do you have a problem with corrosion, slugging, fouling? I'm here, I can help you. No, it's everything fine. This year, actually, the last year is like, the biomass quality changed. We do have problems. Please help us. I think that it can be something that will come in the future when it comes to gasification. We'll have a nice process design, a very reliable technology, but then the biomass change, and then we may have a problem. So it means that it's very up to us to work on the feedstock, to work on the logistics, and to control the quality of the biomass that comes to the plant. Because, for instance, if the biomass quality is bad, maybe we should run our gasifier into this max efficiency mode to limit the biochar production, because if we have some impurities, heavy metals, they will stay there. And then we won't put them to the soil because, come on, it's hazardous. Then we may have some organic chemical components in it, and it's also not good. Then for the gasification, I'm glad that we had today such a great presentation given by Sumitomo. If I had the money, I would buy it. Just for myself, to have it in my garden and to play with it. But we still need to monitor the parameters of gasification to keep the biochar properties good. As I said, the residence time, and then we have the biomass properties, which are very important to produce good biochar. Good biochar, meaning the biochar that has a nice surface area, nice porosity, nice functional groups. There are like many parameters that we have to control, not only to produce a nice syngas at the end, but also to have a nice stable product as the biochar if we want to make an extra revenue by selling that. So if you want to sell it, the third point is that we need to understand the market. As I said, huge competition as well for the biochar in the future. I think that there will be like maybe even oversupply in some areas for the biochar. And then we need to find a good valorization pathway. We need to be in touch with our main client. We need to understand his needs, limitations, and we need to provide the product that will meet all of it. If not, then we have a problem, because we may have a very low value product at the very end, or maybe even in the worst case, we'll have to pay for its landfilling somewhere. And then, of course, at the very end, we need to keep doing research. Innovation is needed. Why? As I said at the very beginning, that we are what we eat. The same is with the biomass that we will provide to the gasification plant. I would consider to have some pretreatment methods to remove impurities that may be there. We have like plenty of options that can be used for that. I can just say that understand the biomass you have, know everything about different fractions. If you see that there is the fraction which is very polluted, get rid of it. Don't use it. You don't want to use this small part of the material that can destroy your final product. The same is for the biochar itself. We can also do the post-treatment of biochar. We can even provide extra carbonization to the biochar. We can use the biochar for the pyrolysis process in order to make it more sturdy, stable, or we can activate it for having a better adsorption behavior. We can even use some microbes to make it more accessible for the soil element. We can adjust pH if we have some issues with heavy metals or impurities. Then we may have thinking about the leaching. So there's like plenty of things that we can do around. But at first, we need to understand what we'll provide to the gasification plant, what we'll get at the end, and then what market needs from us. So thank you very much for your attention. That was all my side.
Okay. Hi, everyone. I'm Tunet Olivier, and I'm here to sort of do, as Paul generally reminds me, the hardest part of all of this project is bringing all of these various sectors together and finding a way to make this plant work anywhere in the world. So, as we all know, greenhouse gases, emissions, they're all a big problem that we're dealing with. And we all know we need to move towards a more sustainable energy solution like biomass. But the challenges that we face are the fact that we have policies and regulations that need to be in place. We have issues with the cost of biomass and competing with other sectors, such as your fossil fuel-based sectors. And we don't necessarily have the economies of scale to be able to compete on a commercial or an industrial scale as we have in the fossil fuel industry. But how do we address these challenges and tip the scales for biorefineries then? So enter the new kid on the block, as they would say. So for this, we'll look at what was the classical definition as proposed by Scherto, where the focus is on traditionally separate industries that can improve their competitive advantage by engaging in the physical exchange of materials, energy, water, and byproducts. And this then is the key, this exchange is the key for collaboration and synergistic possibilities, which is made possible due to the geographical proximity of these industries. So if we then now take these four classical, there we go. If we then go on and we apply this definition of industrial symbiosis, and we can apply it to a biorefinery, then it can potentially facilitate the increase of profitability as well as competitiveness. And it does so by doing exactly as the definition states. It looks at the exchange of waste, energy, cost reduction, as well as looking at the environmental impacts and improving the opportunities for innovation as well as collaboration. So, but what are the challenges that we'll be facing? And I think everyone this morning has actually highlighted the challenges that we will be facing with FlexSNG moving forward very clearly, and also highlighted the sort of potential solutions and the collaboration that we need. One major thing is where we have resource availability as well as the supply chain challenges, where biorefineries rely heavily on consistent supply of biomass feedstock. The variability in availability, quality, as well as the cost of biomass can pose significant challenges. Additionally, logistic issues related to collection, storage, and transportation of biomass can impact operations and efficiencies as well as cost. So what is the potential solution then for this is by integrating biorefineries with a network of industries. Biomass, where we can have access to biomass sources in a variety of sectors such as agriculture, municipal waste sectors, as well as the forestry. This can then stabilize the supply chain and reduce costs associated with raw material, For instance, industries that produce organic waste can directly supply a nearby biorefinery by minimizing transport costs and enhancing feedstock security. Another issue that has also been highlighted is policy and regulatory barriers. And David actually mentioned so beautifully this morning in terms of like in 2024, we're more equipped than what we were 10 years ago to move into this sector, where the challenge is generally that we have that there's uncertainty and unfavorable policies and regulatory environments that can hinder the growth of biorefineries, and industries they lack the incentive for sustainable practices, and there are stringent regulations that might not account for the benefits that you can get with adding a biorefinery. So to swing this, we can then say by demonstrating the environmental and economic benefits of the integrated approach, industrial symbiosis can influence policy development, but it's also collective advocacy from industries that involved in symbiosis that can lead to more supportive policies, incentives for waste reduction, energy efficiency, and development of bio-based products. Next up is the challenges that we face with technological and operational hurdles. And developing and optimizing technology for biomass conversion is complex, costly, and requires extensive R&D development to satisfy the bankability requirements of investors and financiers. Process and operational efficiency is also affected by feedstock variability, as we've heard so clearly. So another way to now address this is by sharing technological resources and expertise within an industrial network, as we've seen now with, especially in FlexSNG, where we've got industry partners working alongside academic institutes to tailor solutions specifically for a technology that is being developed. For instance, and the other thing that we can also have is where one company's byproduct can serve as a valuable input for another company's refinery process, for instance, enabling the development of a more efficient and flexible conversion technology. Additionally, this collective problem-solving approach between industries and technology suppliers and developers can lead to operational improvements as well. So this brings us to my final point, which I'd like to highlight as well, is then the economic and financial risk. So high initial capex investment and uncertain financial returns can deter development of biorefineries. The market for bio-based products is also evolving, and there can be significant price volatilities for both feedstock and end products. However, yet again, as beautifully highlighted this morning, we're moving into an era where the larger industries, such as your aviation, such as your maritime, are feeling the pressure to move towards more bio-based fuel sources. So this is definitely also helping with developing that market for financiers to go, okay, we'll come to the table. So as we've said as well, so the solution for this is definitely collaboration facilitated by industrial symbiosis, and this can help spread that economic risk and provide more stable financial models. So as said, joint ventures, partnerships, these are all allow for the sharing of cost and the development of technology, as well as feedstock supply and product marketing. Moreover, the results of this creates a diversified portfolio of end products that can mitigate the market risk that we can have. So just as a closing remark, implementing biorefineries face challenges such as supply chain, logistics, and economic viability, while using industrial symbiosis can mitigate these challenges by prompting resource sharing, energy efficiency, waste reduction, and collaborative innovation. Through these principles, industrial symbiosis enhances the sustainability and resilience of the industrial ecosystem. Thank you.
Okay, I'm the last speaker for this very interesting roundtable. Thank you for the opportunity to be among you and to be part of this very interesting workshop. I'm Kostis Atsonios. I'm coming from CERT, from Greece. CERT stands for Research and Technology Hellas. It's the largest research technology organization in southeastern Europe. We have 5 institutes and more especially our group is dealing with innovative technologies with the production of advanced biofuels, renewable fuels from non-biological origins, and as well new advanced energy systems with low environmental impact. Today, I have prepared a couple of slides to discuss about the role of the numerical tools and the modeling, the process modeling activities on derisking the FlexSNG technology. Since this kind of activities are, according to the implementation plan, is the last group of activities of the project, because it's strongly relying on the input that given from the pilot and lab activities. I don't have some particular results to share with you, but I will explain more about the impact that these modeling tools and numerical activities have and the contribution that it has on the derisking and moving the technology of FlexSNG forward, and the methodology that we are going to and we are developing on that. First of all, the story of the FlexSNG concept starts somewhere in Helsinki, or some guys from VTT think about this concept that you already heard about that. And the first step after that first concept idea was to prepare a successful application and Europe and in Canada. We got the funding and we proceed to the first kind of the first step in order to move the FlexSNG technology forward. As this is as any technology, our ultimate goal is to reach this technology at TRL 9, meaning that to bring the FlexSNG concept at market and to have an appealing and commercially available technology. As said, the first step has been done. You already heard the interesting results from the technology providers about the endeavor that they paid and the effort they paid in order to bring this technology from TRL 2 or 3 from lab scale to a pilot scale. And now the question that we have to answer is how we're moving towards. How can this very interesting and nice technologies that we have already beneficial impact on the production of sustainable biomethane and biochar can be move forward and be economically available and appealing in near future. Well, and this is the role of the process modeling at first, in order to contribute on that. First of all, what we are doing is to use the mass, all this information given from the lab pilot activities that have been carried out, from the gasification tests, from the reforming activities, for the membrane as well, and of course the supply chain and the methanation processes. These informations are valid and important in order to set up and to establish a process modeling that can be replicated what has been done in pilot level. And then what comes the process modeling to answer is the following questions. The first is up to under which scheme all these technologies can be put together and integrated in an efficient way in order to reach to an efficient operation and operation in full scale. The second is how or can be this FlexSNG competitive to other biomethane technologies production like other gasification oriented or biomethane upgrading from biogas, let's say. These answers that we are going to answer, and moreover, these graphs are indicative from other similar activities that we have done for similar thermochemical pathways. We are going to calculate the carbon balance, how the carbon is distributed along the process, and what is the fate of carbon that is included in the initial feedstock, and how of this resulted in the biomethane. What is how much of this is resulted to the biochar, and what of this is emitted to the atmosphere. Of course, we are going to then to perform the heat and mass balances. This is very important in order to identify the performance of the overall plant. And these informations are very important in order to proceed to the next step of the overall impact assessment of the FlexSNG technology, which is the first step is to develop an appealing and an efficient cost estimation analysis, and to perform the techno-economic assessment of the concept. What we are going to do is under the framework of the FlexSNG project, we have already established 8 interesting case studies from Europe and from Canada, and we are going to see how the technology, the FlexSNG concept fits other different ways in terms of different feedstock valorization, in terms of different scale, and of course in terms of different end products exploitation. And the second step in parallel is also to identify the environmental impact and the benefits that we gain from these new technologies, performing LCAs on these case studies. And then all these information will be get back again to the technology providers and to see what is the tackles and the problems and the obstacles that need to overcome in order to move to the next step, which is the formulation of a demonstration plan, and hopefully to reach in a few years in the industrial realization of the FlexSNG concept. So since I don't have results to present to show to you, I just say that you please stay tuned, and in the following months we're going to present and to show the outcomes of these results and analysis. Thanks.
Over to you. Do you have questions that you would like to ask some of since you've been interacting all this time, maybe you've got some questions of interest for each other?
Actually, I have one question regarding the technology. I mean, the gasifier. Do you think that we can also adapt the concept we have, for instance, to use that syngas not for methanation, but to use that syngas for Fischer-Tropsch synthesis, for instance? Because I mean, we've heard today that there's like a need to provide aviation fuels to the market. So I was thinking if we can use the same concept, but to have another fuel at the end.
In fact, I'm not the expert on this case, but I have here Ilkka, my boss, who will answer this great question. We have done this Fischer-Tropsch challenging.
Yeah, so basically, of course, well, as long as we have syngas, so then we can head to, in a way, directed to various syntheses. So it's possible. Of course, now when looking at the maybe methanol is such that currently we are working quite low pressure process. So then methanol synthesis is typically in very or higher, like 60 to 80 bar. So it might be that in a way the benefits are mainly in SNG and Fischer-Tropsch when looking at the.
Okay, so then I have another question. You can stay there. The second question is for that for the Fischer-Tropsch regarding the capacity. What would be the perfect capacity for Fischer-Tropsch? Because I mean, we've also looked at it and we were wondering what's better to have the syngas plus Fischer-Tropsch and then somehow provide that crude oil. Crude oil to the refinery that will do the last steps, or maybe shall we limit a bit the capacity, so lower also, to take care of the sustainable biomass, because the bigger the capacity, the bigger problem with the biomass we have. And then maybe instead of the Fischer-Tropsch, we should go for the methanol production, and then we take the methanol, and then in a refinery, there is like the alcohol to jet pathway, and then we have the same product at the very end. But let's say, the different capacities, and I was thinking, which one of them can be the proper one? Or what do you feel?
well, maybe it needs a bit more than just like a sophisticated guess, some calculations on background. But the challenge with Fischer-Tropsch is that it will be a crude, which need to be then upgraded. So maybe in cases where there is a suitable place for upgrading, and not maybe on site, but then at some refinery, it can be. The methanol is more easier. It has world markets. You can transport it easier than Fischer-Tropsch crude. So, but I don't have any clear answer. It's case by case.
I'm still happy. Now we have an idea for the follow-up of the FlexSNG.
There, Charles Rand, CanMet Energy in Varennes, Natural Resources Canada. Great presentation, great roundtable. A lot of knowledge around this table here. Just curious if there's any prospects of looking at the integration of gasification technology for, let's say, we hear a lot about the steel industry, about, let's say, if we want to do direct reduction of iron, and it could be hydrogen or even carbon monoxide could be used in that application. And we look in the steel industry, we have the use for, we need to be looking at replacing metallurgical grade coal. So is there an application where you're looking at, could be these two co-products could be produced through, I don't know, whatever series of reactors that could be used on sites or in an industrial symbiosis setup where sawmills are located nearby, pulp paper mills could have some excess residue of different quality wood products that could be going for these applications.
Yeah. Okay. Thank you for the questions. I think that we have also investigated the potential use and evaluated potential use of Biochar in metallurgy and in steel industry. More information, maybe Karol could add after my answer. Moreover, what I can see also as a potential synergy of FlexSNG concept in steel and iron manufacturing is the exploitation of the off gases that could be either converted into biomethane, and the biomethane could be either used again somewhere else in the steel manufacturing plant, or use also or to inject it into the grid, and also valorizing other different feedstock, biogenic feedstock or carbon-based feedstock that now it's a matter of disposal for the steel and iron plant. That's I can see from my side as potential synergy with the iron plant.
The first thing that comes to me is like the quantities. the quantities we would need. And again, I may think about how sustainable that would be, because in terms of the calorific value, of course, you can go close to the coke characteristics. Nonetheless, there is like some inorganic matter which is related to the biomass, and maybe it won't be as good as the mineral ballast you have in coal. And then I would suggest really I mean, maybe you can find a proper one, but it would need some kind of investigation. And so here I would really focus on the quantities you need to provide, and then the properties of the mineral matter, which is in the biochar, that may, I mean, may be very challenging for that use. Regarding using the syngas, I don't know if, I mean, probably the burner would be a very big one if we would like to use it directly. I mean, I know that the colleagues from the other group at EIFER, they work on the hydrogen use for that purpose. And probably that would be more sustainable if you think about the logistics of the biomass sourcing. But on the other hand, if you have the specific case in which you have a lot of residues, it's worth to consider it, of course.
Thanks for the answers.
I'm ready for another comment from the panel on the way you responded, Karol, to a question or asked a question about the sustainability of biomass and economies of scale. So as a cynic, and then maybe asking others who might have a different insight, I would say that you can't get it on the assumption that gasification is got a strong economy of scale, which it does. You just can't get big enough. So as long as you harvest sustainably and it's economically available, we always go bigger. And history has shown that, whether it's a craft digester or a recovery boiler or no matter what it is, and that there's a bit of misinformation about that, because when we're developing a capital intensive process, we don't want to redesign for a larger scale because the risks are huge. The investment is huge. And so we say, well, we don't need to go bigger than 400 tons a day of dry matter because, you know, we can't get more than that economically. And that's just not true. So bigger is, I think bigger is better, and it's the risk going bigger. But the sustainability and the biomass availability side of it, any comments on that, or does somebody say something on the process that may be counter to economies of bigger is better? Yeah, Andrew.
I was interested, Minna mentioned about pressure, and you also touched on pressure for the thing. If we make a lot of pressure, will that be a big improvement? Will that be able to bring the size down? And what are the prospects for pressure in the system?
I can comment for the OTM specifically, and we've seen from data from the producer that pressure, higher pressure, operative pressure, increased the flow of oxygen through the membrane because they changed the partial pressure and the total pressure with it. It might complicate the system in terms of safety and handling of pressure and these kind of events, but it will definitely make it more compact, because then you need less active area of the membranes, and I don't know how it would impact whether negatively or positively the gasification in particular, but for that matter, it's a worthwhile test to do.
Ilkka, is that so that we have used in validation test around 2 bars and not above? Yeah, we have run the gasifier. I think there are some limitations.
Just grab a seat and
Sure. Yeah.
So basically, the pressure of the gasifier, that's of course goes then a bit like the feeders, the biomass characteristics, how to feed them if you want to go to like 10 to 20 bar pressure. It has been done as David showed in Sweden, for example, in 16 bar, and there are some technologies which work in high pressures, but then it needs maybe some densified biomasses and feedstocks, which might then be a drawback. But it's, of course, if you want to go, for example, for methanol production, if you start from atmospheric pressure, you need like a 3-stage compressor to get into those, and then you can save maybe 1 stage if slightly pressurizing the gasifier.
Yes, if I may, I can also comment on that. Of course, from an energy perspective, it's much more efficient to operate the gasifier at elevated pressure, and in order to avoid the compression in the next steps, etc. But the feedback that we get from technology providers like Sumitomo Foster Wheeler in these projects is that their clients now shift to the commissioning and they order atmospheric gasifiers, and the reason is one because the atmospheric the pressurized gasifiers has a very high maintenance cost, because in case that you want to something goes wrong in the process, you have to shut down the overall plant, and in order to make an maintenance or replacement or something. So they prefer to avoid that part and to pay more compression costs downstream in the process rather than have that issues during the operation.
Good morning. Serge Bédard, Natural Resources Canada. In terms of biochar, any idea of the properties you might be able to reach in terms of quality? Are you targeting mostly soil abatement or carbon sequestration period, or would you try to go to more fancy applications in the future? Which is a big challenge, but a huge need at the same time.
Yeah, I mean, at the current stage, we were considering 2 utilization pathways mainly, and because I mean, according to the properties we've seen, so it was like to use biochar for energy purposes because of its composition. Then we also think that we can use that biochar for carbon sequestration, I mean carbon sinks, but more like to put it to the some materials, maybe to use it as the filler for the concrete. For the soil amendment, we still have some issues that we should solve. It's like this organic components that we don't want to have there because they may pollute the soil too much and they are like the toxic. So it's something that we really have to pay attention to. Maybe some extra post-treatment would be required for that. I also see like another possible utilization pathway for the biochar, even maybe the biochar with no separation after the gasification, so we can take even the biochar with the bottom ash or the fly ash, wherever we take it from, to use the biochar as the additive for combustion, because in terms of its composition, there are some elements. I talk too much and they just. Yeah, it's like you're done. I used my tongue today. So I see that maybe we can use also the biochar as the additive for the biomass combustion, because the biomass combustion, as I said before, there are some challenging issues in terms of the composition of the biomass, like the chlorine content, especially the chlorine content. And then the biochar is full of alkali, like the good alkali with the high ash fusion temperatures. Then I also see this as the possible utilization pathway. So at the current stage, I mean, at least for the FlexSNG concept, to use it for the energy purposes, to use it as the filler for some materials, that would be fine. For the other uses, I would need to have more research conducted on that matter.
Thank
Thank
you.
you.
Just maybe as a complementary, well, as an information, in the province of Quebec, the steel industry, the cement sector, and the aluminum sector could use all the forest residues available just for its own need for biocarbon. So that's definitely an interesting and promising area, but it's really a difficult high grade and difficult quality to be produced. So
Yeah, I mean that I mean that's correct. I mean at least in Poland, all the carbon, I mean all the waste we have, RDF, SRF, or the biomass, it's like cement plant. Just please give it to us. We'll take care of it, and that is why the other plants have a problem with the biomass logistics or the waste logistics. But yeah.
So for that simple reason, simple point that you're bringing, some people are arguing maybe we shouldn't try to get to these fancy renewable, sustainable fuel for aviation and just do this biocarbon and biochar and torrefied pellet for cement and steel, and they will take it all, and we don't have enough anyway.
Yeah,
so that's
but
an interesting.
Then how will drive the car? How will go? How will fly to Europe?
Yeah,
It's like,
sure, but if
there
we
is
do
no.
those, no, yeah, I agree with you. But if we do those, there is not enough for the other sectors.
yeah,
So overall, there is not enough. That's
that-
the whole point.
That's correct. That's why I also said that we will really struggle to get the good quality biomass for our process. So maybe the process we'll have at the end has to be very flexible in terms of the biomass or the feedstock we'll provide to the process. Maybe the blending is the solution. I mean, the best pellets we burned in our plant, they were like the green mix. Green mix was the best. I mean, it was not good, but it was stable. We needed how to deal with it. The problem was when we changed the quality, like from the good to the bad one. So then the operators, the boiler operators really didn't like it. So I think that's probably the same would be for the gasification.
Thank you.
I have one. In terms of, okay, so we're running trials and we're running campaigns at this point in time with the gasifier. How easy is it to switch from one feedstock to the next feedstock and have those campaigns where you have like, okay, you know, over the year, if you take a look at that year period and you say 50% of my feedstock's coming from forestry, 30% is coming from municipal sectors, and like the other 20% is coming from agricultural. How do you account for that switch? And is it where you say I can only take in a certain capacity, and whatever is left, now we don't know what to do with it based on the location?
If I answer about our test pilots and the flexibility of feedstocks changing, I think it's kind of flexible and it will be carried out quite easy. So there are no problems. We just change the feedstock and.
Okay. Does it require a complete shutdown?
No.
Well,
We just we had a kind of feeder where there is two feeders, one below and one above, and then we put a new feedstock in the higher feeder, and then it's waiting there to come down when the lower feeder is empty.
Okay.
And it goes very flexible.
Okay.
Yeah.
It's a matter of hours, right?
Yeah, it takes several hours. Yeah.
Okay.
Yeah. For example, our earlier validation test, it took was it around 6 hours or more? Ilkka? Around that, yeah. Now I know. Yeah. It was around 6 hours to change.
Okay.
Thanks.
6 hours, are you?
We are out of our set points then. This is not our set point. Our set point when we do all the samplings and measurements starts when the new feedstock is running and the operation is stable, process parameters are stable. Yeah.
either flare the product or recirculate things.
Yeah,
6 hours is a long time.
yeah.
They switch between the two, I guess you could. Biz, you could.
Yeah, Tom Brown, I'm a consultant. Very interesting morning. The comment I would have, having spent all my life in the pulp and paper industry, is that if you're going to go build a plant near a forest industry, facility, and then you draw a circle of radius 200 kilometers, you're only going to find wood. You're not going to find ag residues. And same thing if you go build in the prairies, you're only going to find ag residues. You're not going to find wood. There are a few places where you might find both. And if you put it in Montreal, if you draw a 100-kilometer circle, you're only going to find municipal solid waste. So do you really need a plant that can swing? What you want is a process that can be designed to run on one, build it to run on one, it'll run well on that, and then the plant that goes somewhere else will be designed to run on something else. And then you can have feed systems that are optimized for either chips or long stringy grasses that'll plug screws and bridge bins. I mean, as it is, the pulp and paper industry has a hard enough time swinging from hardwood to softwood and back, which are both chips, and it's all wood, but it's an 8-hour transition where you're making off-grade pulp when you do that. So, just a thought for the future about the importance of being able to swing.
Case studies, there's 8 case studies that I think is looking at. They all have the people swing conditions. Right? So the Canadian one is Greenfield Local. And so you've got 100 kilometer and a 200 kilometer radius, but then you've got barges from North Shore and the South Shore. So a different mode of transportation. But if you need economy of scale, the higher you go, the harder it is to get to.
Our biggest pulp mill is 1 gigawatt feed capacity. The feed going into Canada's biggest pulp mill is 1 gigawatt. It's never going to be bigger than that because you can't get wood any faster, any further.
I think just talking aloud here, there is examples in Sweden where you are in the south of Sweden where you have access to agriculture and forest residue.
A different case.
Because the problem with the forest residue is it's quite high in demand. So you plan with agricultural residues to lower the cost because the competitiveness is too high for the forest residue overall within the area because you have so much bioenergy being produced by forest residue. So that's another example.
Yeah, not the case of Canada.
No.
I can also add to that. I remember that when we started the biomass combustion in Poland, so in 2008 or 9, we had 100% of wood chips. The wood chips and wood pellets. Then, due to the high consumption of the biomass on the market, we ended at the very end with 80% of agro biomass and 20% of woody biomass, and we imported the agro biomass even from Ukraine, and just to be able to operate the plant we had, because at the very beginning we didn't even thought about such huge logistic problems, but then then the other power plants operators had the same idea to burn the biomass, and at some point we just had no more biomass on the market, and we just took everything. So that flexibility, it's at some point, at least in Europe, it's needed.
The audience for the questions and for your time all morning. That was a great session. This afternoon for the energy management.